Hello, for this problem, we've got a 60 kilogram wheelbarrow, dimensions shown below, and is subjected to a pulling force on the left. So if we assume that there's no friction at the wheel at B, we've got a static coefficient of friction at A, assumed to be 0.4, what is the expected pulling force needed to get the wheelbarrow moving? So this one's a little bit different than previous problems in that we've got 2 points of contact, but friction only exists at one of those 2 points. So this is going to be an equilibrium analysis problem as well as a friction problem. So I've already kind of drawn an outline over here on the right of my wheelbarrow, and I'm going to kind of fill in the rest of my free body diagram here. So first thing I'm going to do is add the forces. So I'm going to have F pull over here on the left. I'd have a gravity force here in the middle, and that's going to be 60 kilograms times 9.81. Convert that to newtons. I'm going to have a normal force at both A and B. So F and A, F and B. And then finally, I'm going to have a friction force that exists only at A. So that is going to be going to the right because it is opposing motion. So if I'm trying to pull it to the left, friction force is going to the right. So to add to my free body diagram, I'm also going to need to add some dimensions. So this distance here from the ground up to the pulling force is 0.7 meters. The distance from A over to the gravity force is 0.8 meters. And then the distance from the gravity force to the front wheel is 0.6 meters. So with all of that, I've got my free body diagram. I'm going to go ahead and just specify my X and Y directions here real quick. And then let's jump to the equilibrium equations. So first one would be sum of forces in the X is equal to 0. So sum of forces in the X, well, I've got friction force going to the right. I've got the pulling force going to the left, and that needs to add up to 0. Next up, I've got forces in the Y, so sum of forces in the Y. I've got normal force at A, so F and A, plus F and B, both of those are going up. And then I've got my gravity force going down, so minus 60 times 9.81. That needs to add up to 0. Next up, I'm going to have the moment force, or the sum of moments. So sum of moments, I'm going to do about point A, and again, point A is the left-hand support, so not the wheel. So sum of moments about A, the pulling force is going to exert a moment counterclockwise, so F pull times 0.7 meters would be the perpendicular distance. The gravity force is going to exert a clockwise moment, so that's negative, so minus 60 times 9.81 is the magnitude, and the distance is 0.8. And then finally, the normal force at B is going to exert a counterclockwise moment, so it's positive, so plus F and B times the total distance of 0.8 plus 1, or 0.8 plus 0.6 is 1.4 meters. All right, so we have our 3 equilibrium equations. One thing we're going to notice, though, is that we've got friction force, pulling force, normal force A, normal force B. We've got 4 unknowns that are showing up in our equations. So 4 unknowns, 3 equations, this is not going to be solvable. We can fix that, though, by treating this like it is a wheelbarrow at impending motion. So right at the moment it starts moving, the friction force is going to be mu static times the normal force. In this case, mu static is 0.4, and the normal force is specifically F and A, because friction force only exists at at point A, not at point B. So this last equation here, Fn, basically, or not Fn, sorry, friction force, So FF is equal to 0.4 times FNA is my last equation. So 4 equations, 4 unknowns. This is solvable now. All right, so we're going to go ahead and solve these. And the general strategy I'm going to take is I'm going to basically rearrange the sum of forces in the x, sum of forces in the y, and then plug those into the moment equation to solve for FNA. All right, so for this, my first equation is going to be FF, which is equal to F pull, is also going to be equal to 0.4 times FNA. So F pull is equal to 0.4 times FNA. The other equation I'm going to do is the rearranging sum of forces in the y, and I'm going to say that FNB is going to be equal to 588.6, that is 60 times 9.81, minus FNA. That's my second equation, and both of these are going to get substituted in to the sum of moments about point A equation. So first thing is going to be F pull is replaced with 0.4 FNA times 0.7 minus the middle piece, so 60 times 9.81 times 0.8. That just reduces down to 470.88. And then the last piece is going to be, so FNB, I'm going to replace that with plus 588.6 minus FNA, and that gets multiplied by 1.4. So now I've got one equation with only a single unknown in it. So reducing this down, 0.28 FNA minus 470.88 plus, so 588.6 times 1.4 is going to give us 824.04 minus 1.4 FNA is equal to 0. Do a little more consolidation. I find that FNA is going to be equal to 315.3 newtons. All right, so from here, I can say that, well, FF, the friction force, is going to be equal to 0.4 times FNA. So 0.4 times this 315.3. My friction force is going to be equal to 126.1 newtons. And lastly, my pulling force was equal to my friction force, which is equal to 126.1 newtons. So this is the force required to get the wheelbarrow moving. It is 126.1 newtons. All right, that's all we have for this video example. Thank you for watching, and I hope to see you again.